So today we are going to talk about proof test planning and how exSILentia helps guide you through your proof test planning. So basically, during SIL verification, you define a testing strategy. And when you do this, there are certain things that should then dictate the procedure you go and do your testing on your devices with during the O&M phase. So in this webinar, I'm going to take a deep dive into exactly how your proof test strategy affects your SIL verification calculations and how you can move forward and ensure that you have a procedure that is ensuring your safety integrity that you've achieved. Now, before we dive into all that, I should introduce myself. My name is Kate Hildenbrandt. I am product manager here at exida for exSILentia. So that means I am responsible for feature definition and product roadmap, as well as training and customer support. For that reason, I have my email address here. Feel free to contact me with any questions you have about our software tools and, of course, exida at large. Speaking of exida, just a little overview. Some of you might not be familiar with what we do here. Obviously, I'm talking about exSILentia today, which means that we're focusing on our enterprise tools. We do have software products for functional safety, for alarm management, and for cybersecurity. We also have a lifecycle services group. So this is our group of consultants that tackle the same functional safety, cybersecurity, and alarm management tasks. So if you need a solution for that, if you're looking for help with any of those tasks, we can help you there. We also have a certification group. They certify devices used across the industry for safety instrumented systems. And we also certify personnel. So if you've heard of the CFSE or CFSP programs, that's us. We also have a similar certification program for cybersecurity. And these groups work well together within our company. Our consultants do use our software tools, and our certification group allows us to embed data, for instance, our failure rate data, in our software tools so that you can have a streamlined work process to choose your equipment and have those failure rates automatically filled in and perform your calculation. So hopefully exida has your consulting or software solution that you need, and we can help you with any of your safety needs. We also have locations worldwide. So I personally am located in the Sellersville office, which is right outside Pennsylvania in the US, but if you take a look at the map, hopefully you can get in touch with an exida representative more locally. So I'm going to start with a high-level look at the safety life cycle, and hopefully this looks somewhat familiar to you. It is the safety life cycle as defined by IEC 61511, and it is providing a method to analyze, implement, and maintain a safety instrumented system. This starts at project scope definition and ends at decommissioning of your plant. And those familiar with this know that it's broken down into 3 different phases: the analysis phase, the design phase, and the O&M phase. When it comes to the different tasks in the safety life cycle, there's a nice flow, especially when you're focusing on safety instrumented functions, through the analysis and design phase. It usually starts with the process hazard analysis, and in this task, you're taking your process, you're going to split it into smaller pieces, so units and nodes, and for each node, you're going to take a look at any challenges to the process parameters. When I say a challenge to the process parameter, obviously I mean, what if your process parameter is pressure and it gets too high or too low? Perhaps your process parameter is temperature or flow. Any challenge to that process parameter that cause a hazard is something you might want to focus on and implement safeguards for. So in the PHA, you are documenting causes, consequences, safeguards, and any recommendations for further study for any hazard scenario. Once you've identified those hazard scenarios, you might move on to do a layer of protection analysis. And in this case, you take these safeguards, determine which are independent, and you're identifying if you have enough protection against your high-risk scenarios. In some cases, you might find that you do, that you've met all your target frequencies for those hazard scenarios to occur. But if you don't, you might want to add some protection layers. Some of these protection layers are going to be safety instrumented functions, and some of them might then, after the LOPA, have a risk reduction factor that you want to target during the design. This is determined in your SIL selection, so you're determining the SIF integrity requirements, and it's also communicated in your safety requirements specification, where you're documenting all the SIF design requirements for implementation. The SRS is meant as a handoff to the design team, and they're going to do the SIL verification or the design calculations. So you determine your conceptual SIF design during this task, which means you're choosing your equipment, you're choosing your SIF architecture, which means do you have any redundancy in your SIF, and you're determining your testing strategy. So in SIL verification, again, this is the conceptual SIF design that you are specifying. And your integrity requirements are based on 3 different things. Once you model your SIF, it's going to calculate the SIL based on PFD average. It's going to determine the SIL based on architectural constraints, and the SIL level based on systematic capability. So for architectural constraints, we want to make sure that we have enough redundancy in our system. And for systematic capability, we want to make sure that the equipment used is appropriate for the application, and that you know exactly what accurate data is going into the calculation as far as failure rates go. Now, the SIL based on PFD average is what we're going to focus on today, because that is affected by certain factors. Obviously, the failure rates, as we talked about, with the equipment that you are dealing with, the failure modes, but also your testing strategy. So we're going to dive into this in more detail, but you can see here that your proof test frequency and proof test effectiveness are going to have an impact on your design calculation result. So what does this mean? What do we mean by proof testing? What do we mean by frequency and effectiveness? We're going to start at the very beginning and look at different failure modes. So when you choose a device, that device is inherently going to have certain ways that it can fail. And some of these failures are going to be dangerous and some of them are going to be safe. Well, what do we mean by that? A dangerous failure is a failure that prevents the device from responding to a potential dangerous condition. So if your device is failing in a way that the SIF cannot achieve the safe state anymore, this would be a dangerous failure. And we classify these dangerous failure of a device as called lambda D. For a safe failure, this causes a device to go into the safe state when no hazard is present. And that's why we would call it a safe failure. It might not cause a dangerous scenario to occur, but it is shutting down the plant while it's supposed to be running. A safe failure in this case is called lambda S. So let's look at a little example of this. Let's consider a furnace example. So you have a valve on the main fuel line into a furnace, and it's open during normal operation. So it's providing fuel to the furnace. To achieve safe state in the event of a hazard, the valve has to close. And obviously, if the valve closes, the flow of fuel to the furnace halts. So obviously, take a look at the picture. The valve remains open during normal operation, but if there is a hazardous event happening, the valve is going to close to achieve the safe state. What would a dangerous failure be in this scenario? Well, a stuck stem is a good example of a dangerous failure. In this case, the valve can't close. and the fuel is going to continue to flow into the furnace and could cause a possible explosion or hazardous scenario. In this case, you might damage some equipment. You might have, unfortunately, injuries or fatalities that take place because of a dangerous explosion. So that would be your dangerous failure in this scenario. What about a safe failure? Well, an actuator leak is a good example of a safe failure. In this case, with loss of instrument air pressure, the spring will force the valve closed during normal operation. So this is a scenario where there's no hazard, but the valve itself is closing, halting production, and you're probably not going to have anybody hurt. It might not be a safety event, but it might still cost you some money from a business perspective because your plant is down. You're not being productive there. So that is an example of a safe failure. Now, these safe and dangerous failures can be further divided into detected or undetected categories. This accounts for the ability of automatic detection or diagnostics within a device to reveal failures while the plant is running. So as I said, they can be classified into 4 categories with safe detected, safe undetected, dangerous detected, and dangerous undetected. So depending on the device that you're choosing, if it's able to detect those failures during normal operation, you might be then mitigating some additional hazards. So any of the safe detected or dangerous detected failures would be maximized by choosing a device that can have automatic detection mechanism to reveal those failures. But in this case, we now know that we want to focus on the dangerous undetected failures to maintain the safety of our process. So obviously of the 4 failure modes, dangerous detected failures prevent the SIF from performing without operator awareness. So this is the scary kind of failure. For this reason, these failures are most dominant in determining the SIF's overall safety integrity. So this is what we're focusing most on in SIL verification. To further reveal dangerous undetected failures, periodic manual tests are performed, usually while the plant is down, to ensure SIF components are functional. So keep in mind that when you implement a safety instrumented system, you're putting equipment in your plant that is mostly just sitting and waiting for a hazard to occur. It's not the same as your control system, which might be performing and moving quite a bit. So a lot of the failures that occur within a safety instrumented system occur to devices that have not been moved or used in a while. I always like to think of it like my car. If I'm driving my car every day, I'm pretty certain when I go into the driveway in the morning that it's most likely going to turn on when I press start. If I haven't driven my car for months or a year, I'm a little less sure that it's going to work when I try and turn it on. And the same goes for the devices in your safety instrumented system. So if we look at the probability of failure on demand as a function of time, when you're installing your equipment, we assume that your infant mortality failures have already been sussed out during the testing phase. So when you do your FATs and your SATs, we assume any of those initial failures are being weeded out, that you have a device that is brand new and there's very, very low probability that it's going to fail on demand. But over time, as it sits there, we're less and less sure. So probability of failure on demand is increasing over time. As you can see, we also take the average, so that dotted black line is taking the average of your probability of failure on demand over the mission time. In this case, that's 15 years, and that's the time that the SIF is in service before it's completely refurbished or replaced. So this is your PFD chart without any testing. This is just how it would go if you installed the equipment and let it run for 15 years. In many cases, when we want to achieve our target design criteria, we might need to implement that manual testing. So you go out into the plant, most likely your plant is shut down. Sometimes people have bypass so they can do it while the plant is online, and that's great. But you're going out and you're moving that equipment, you're testing it out to see if it's working correctly. And when you do that, there's dangerous undetected failures that can be revealed. Perhaps you're replacing equipment, but if it works, your probability of failure on demand is going to go down. So here you can see the impact of proof testing on the PFD. In this scenario, a proof test is being performed once a year, and you can see that dip in the probability of failure each time a proof test is done, that it increases from there until the next proof test is performed. So this is bringing that PFD average way down because by doing the functional test, you are ensuring that that device is working when there's a demand, or that you're revealing any failures and fixing them before a hazardous scenario is present. So here you can see the impact of proof testing on the PFD. Well, let's talk about how frequency affects the results. The frequency of testing is often input into your SIL verification as a proof test interval, their time between proof tests. And the probability of failure on demand increases over time, as we saw, but decreases with each proof test that's performed successfully. So your PFD average is pretty affected by this proof test interval. As you can see, PFD average equals lambda DU, which is dangerous undetected failure rate, times the proof test interval over 2. So if we do a proof test every year, as we saw earlier on the chart, we're going to get that dip in the probability of failure on demand each year. If we do it every 5 years, that's going to happen less often. So you can see how that's impacting the average. The more often you do the proof test, the lower the PFD average is going to be. That said, it's hard to always be doing functional tests. The testing frequency is limited by the time and cost constraints. So if you're shutting down your plant, you're not really maximizing uptime. Obviously, we want these plants to be productive. So shutting down your plant is something you don't want to have to do too often. Additionally, there's a labor cost. You have to send a tech out to do, or an operator, someone to do the testing, and that might be taking them away from other things. Depending on the size of your safety instrumented system, you could be testing devices all the time, and that might not really be ideal to reach your goals on your site. So keeping in mind that more frequent proof testing is a positive when it comes to lowering the probability of failure on demand, it also has to be balanced by realizing there's a cost associated with each proof test. So ideally, in the SIL verification, you can optimize this and determine what proof test frequency is needed for each of the SIF components. Let's take a look at proof test effectiveness. What do we mean by this? Well, not all proof tests are created equal. Depending on your procedure, depending on the device you're working with, your proof test is going to reveal some fraction of the total dangerous undetected failures that you have with that piece of equipment. More extensive proof tests are more effective. So if you're doing more to test those different failures, you're going to improve the safety integrity of the SIF design. At some point, there's not much more you can do to reveal those failures, but that effectiveness is represented by the proof test coverage. And the proof test coverage factor is basically the percentage of dangerous undetected failures that are revealed during a proof test. So as you can see in the equation, your PFD average is now split up between dangerous undetected failures that are revealed during the proof test times the proof test interval over 2, plus the dangerous undetected failures that are not revealed during a proof test times the mission time over 2. What this is saying is, depending on the test that you're performing, so the literal steps that you take to do the functional test and reveal any failures, perhaps you didn't realize you could test in another way, so you can add on to the scope of your proof test and reveal more failures. Or perhaps you just have a piece of equipment that fails in such a way that you can't necessarily reveal by functional testing at all. The proof test coverage is often not 100%. So we get out there, do the functional test and reveal as many as we can, but this is a pretty good measure of the effectiveness of the proof test. Let's look at the impact on the PFD charts. In the first chart here, you can see that the sawtooth that we've been looking at is pretty consistent. And this is showing something close to a coverage of 100% for your proof test. And the probability of failure is almost resetting each time, meaning that your dangerous undetected failures are being revealed almost 100% every test. Again, this is rare, but this is what it would look like in a PFD chart. And in this case, the PFD average is nice and low. More likely is that you have a coverage that shows you can't reveal all of your dangerous undetected failures. And so it's not resetting each time, but in the second chart you see that it is decreasing over time, but less and less because you can only reveal so many failures. So over time you're still decreasing the PFD average, but this is more likely what's going to happen. The more effective the proof test, the lower the PFD average. This is sort of best described by some of the different testing you can do with a final element. So if your proof test coverage depends on the device's DU failures and the test procedure, then you can apply this basically to your final element assemblies, your solenoid actuator valve. There are 5 different tests we've identified that you can do to reveal some of your dangerous undetected failures. Proof test 1 is a partial valve stroke test. In a partial valve stroke test, you're moving the valve basically 5 to 10% of its total stroke, and you're recording the duration. This is a test that you can do while the plant is running pretty easily. You could even initiate it automatically. And for that reason, it's helpful if you're trying to increase your uptime and not shut down the plant to do or implement any bypasses to do a functional test. That said, it also doesn't reveal as many failures. You're going to reveal more failures if you do proof test 2, which is a full stroke test. So you're moving the valve 100% of its full stroke and you're recording the duration. Because this is done manually or while the valve is on bypass, you can also perform a physical inspection. So more failures, more dangerous undetected failures are going to be revealed with proof test 2. But you can do even more. So proof test 3 is full valve stroke test at operating conditions. Proof test 4 is full valve stroke test and a leak test. And then proof test 5 is full valve stroke test and a leak test at operating conditions. So obviously, the effectiveness of proof test 5 is going to be highest because it is revealing as many dangerous undetected failures as possible for your final element assembly. So here you can see that by increasing the scope of the test, you can increase the effectiveness of the test. You can see how the procedure itself is going to directly impact your results. And just a note, you know, a lot of the data that backs this up is determined using FMEDA analysis, so failure mode effects and diagnostic analysis. We do this at exida. Our certification group certifies devices, determining their failure rates, their useful life, proof test coverages, so on and so forth. So that's how proof test effectiveness is determined. And if you take a look, this chart sort of shows you for different devices what the functional failure mode is, what the dangerous failure rate is, and then for each of these tests, what failures are detected by the test. So we remember PT 1 through 5. If you look at the solenoid valve at the top, your functional failure mode is loss of drive. The dangerous failure rate is 230 fits. And then each of the tests detects a certain number of those failures. For PT1, our partial valve stroke test, you are detecting 207 of the dangerous failures. But you see, starting with PT3, it bumps up to 228. So as you study the chart, you can basically see how the different proof test procedures and the scope of those procedures are affecting the test coverage. At the bottom, you can see the test coverage is 51% for PT1 and 99% for PT5. So that's a good look at exactly how the scope of the procedure can affect your coverage and therefore have a big impact on your PFD average and your achieved SIL. So how do we tackle all of this when we're actually doing the design and proof test specification? exSILentia is a tool that obviously helps with this. You do in your SIL verification input these proof test parameters. The first one would be your proof test interval, which is your time between tests. But you can also indicate your proof test scope. So as we talked about with the final elements, you might do a full valve stroke test and also include a leak test and do these at operating conditions. This is going to affect your proof test coverage. One thing I want to highlight when using Silver, if you're choosing a piece of equipment from our failure rate database, that piece of equipment comes with a proof test coverage. And the reason we know the coverage is because there's an associated proof test that comes with the piece of equipment in the database. That proof test is often provided by the equipment manufacturer. And it's literally a list of steps saying do this, do that, do the other for your functional test. If you do those, your proof test coverage is based on the number of dangerous undetected failures you're going to reveal during that test. And all of that is embedded in the tool. So when you choose your equipment in Silver, you can simply hit that proof test coverage calculator and it's going to give you the correct coverage. Now, if you know that you're doing more than that test is laying out as a procedure, you can obviously go in there and manually change the proof test coverage. You can see partial valve stroke test can be enabled as well in the tool. You can set the interval, the duration, the coverage, say if it's initiated automatically, and so on. Silver also allows you to indicate if your test is performed online, if you have alternative protection, and what the duration of the test is. So your whole strategy is mapped out in SIL verification. And what we want to ensure is that when you move forward into the O&M phase, you're actually doing these steps that back up the data that you put into your to your calculation so that you're actually achieving the safety integrity that you believe that you are. So one thing we do in exSILentia is all of those proof tests that are associated with the devices are embedded within the tool. So we've created a proof test generator, and this proof test generator gives you suggestions for each of the devices. These are the steps that are embedded in the database. You can choose to apply them. You can apply them one at a time or all at once, and you can go into the proof test procedure editor, and you can add any notes that you want to. You can add pass-fail criteria, anything you want to do to create a proof test that is usable for you at your site. Steps can be added, reordered. It's very, very flexible. And then once you're done, you can generate a report in Word. You can also import this into our SILstat tool if you are a user of our O&M tool, which allows you to record directly into the software as you're doing the proof test. But as is, this is hopefully going to make it easy to carry out your functional test in a way that really validates your calculation and makes sure that your strategy for proof testing is being carried out as needed. So I am going to open the tool and show this to you directly. And one thing I always like to do is show what it is I've modeled in my sample project. I already have modeled this SIF in Silver, and I've done it a few times. So this specific SIF that I'm showing here is modeled in Silver 5 times in the file I'm going to open with the different proof test options. So for the final element, 1 is just PT1, SIF 2 is doing the second proof test, which is full valve stroke test. 3 is doing that at operating conditions, and so on and so forth. So just to take a look at what the SIF is, it is a in my sample, I called it a high pressure SIF, but it has 3 SIL certified pressure transmitters, voted 2 out of 3, a generic SIL 3 certified safety PLC, and a floating ball valve driven by a spring return rack and pinion actuator, driving by a 2 out of 3 port pilot operated solenoid. So a pretty straightforward, simple SIF that we'll take a look at. So we're going to do that demo. So hopefully now you see exSILentia on your screen. This is just the dashboard. You can see up top we have all the different modules lined up. We're going to dive right into the Silver module. And here are the SIFs that I just mentioned. Again, this is the same SIF that you saw in the diagram, but with different proof test strategies for each one. One thing I want to show for the sensor part in SIF 1, you can see the proof test interval is 5 years. We have a coverage of 91%. It's not performed online, and we're not doing any application level diagnostic testing. For the SIL certified PLC, we have a proof test interval of 5 years and a proof test coverage of 90%. And then for our final element group, we have a proof test interval of 1 year, a coverage of 59%. Here you can see you can enable the partial valve stroke, and I want to point out that you can determine which of these the test is actually performed on. So here we have modeled a 3-way solenoid, a pneumatic rack and pinion actuator, and a floating ball valve. And so when you enable the partial valve stroke, we assume that it's affecting all 3 of the devices, but perhaps it's not actually revealing any failures in the solenoid, so you can indicate that here. The way this has been done is the actual proof test is showing a coverage that coincides with the partial valve stroke test. So we're not going to add the embedded tool PVST test here. But if you look at SIF2, if you go down to the final element part, you have that full valve stroke test coverage. And then for 3, it's at operating conditions. 4 is going to have a leak test. Let me find it. You see that leak test box is checked. And then 5 is going to include full stroke, leak test at operating conditions. So full stroke coverage, leak test at operating conditions. So you can see you have the same SIF. It's going to, but with a different proof test strategy, is going to affect your results. We can highlight that by showing that the proof test for the proof test 5, the most extensive proof test, has an achieved risk reduction factor of 47.5. Without the at operating conditions, it's 38.7. Without the leak test, it's 21.5. Just full stroke is 28.9. And just with that partial stroke, it's 12.9. So you can very clearly see it in the results, how the proof test strategy is affecting your achieved SIL and RRF. So that's how we determine the proof test strategy in Silver. Now, as I said, with each of these devices, you have an associated proof test that is determining that proof test coverage that's calculated here. So if we take a look at this rose mount, for instance, you can actually see the proof test steps that are associated with it. Again, most of these come from the manufacturer, but it is a property of the device within exSILentia. So this is the proof test that is supplied by our Safety Equipment Reliability Handbook. It's pretty straightforward. But you can see that you can also add a step. So the library allows you to add any step. So perhaps on your site, every time you have a rose mount, you do a specific step that you want to add here, so that when you create your proof test procedure, it's going to be added in the suggestions and can just be added to the editor. But it is a property of the device itself. And so when you go into, if you're done with your SIL verification, you can go over here to the proof test generator. And for each of these tests, as I showed you earlier, we have proof test suggestions for all of the devices in your SIF. And these can be applied all at once or one at a time. So if I go down to SIF 3, I have not yet created my proof test. I just have my suggestions. In this case, I can say I want to apply all of these because I know this is the basis of my calculation. I can come in here and give it a name. SIF3 proof test. And you can add here any steps that you like. You can add sub-steps. So if I say ensure proper PPE is on before entering site, just for an example. And you can say sign in with operator before entering site. You can put in any application specific or site specific steps that you like in here. We really want this to be useful to you in a way. We know that a lot of our users already have proof tests that are defined. And in that case, you would be able to import them in if you wanted them here in the tool, or if you wanted to basically keep it consistent with your SIL verification. So when you come back and do a validation, did you update your proof test coverage, and therefore your proof test steps should be updated too. So you can do that here. You can add a description if you like. You can say who the author is from your team members, give it a status. The other thing you can do is you can add pass-fail criteria. So that's what this layout is. So say that you are doing your test and you know what number this should be. So when you send a heart command to the transmitter to go to the high alarm current output and verify the analog current reaches that value. So say in this case, you want this value to equal 21.5. You can give it a tolerance if you like, and that's milliamps. Yep. And you can save that. So that's a way to make sure that you know what your pass-fail criteria is. If you do import this into our SILstat software, it's going to automatically let you know if you passed or failed based on this. But if you're just generating a report, or perhaps doing it in a different tool, say SAP or something, this might be useful information to you. So once you have determined all of your proof test procedures, you can generate a report. And this is going to generate in Microsoft Word. All the reports for exSILentia generate Microsoft Word, and all the data exports generate in Excel. So in that case, if you have any editing you'd like to do here, say you'd like to put your own company logo where it says exSILentia, no problem at all. And the proof test procedure report is going to list the different SIFs or proof tests included in the report. It shows the different devices as well as the proof test interval that was used in the SIL verification for each part of the SIF. If you added a description, it's going to show it here, but it also gives a place for testing date and the person responsible. So if you're printing this out and taking it out to the plant, you can fill that in there. And then all your steps are there. You can say if it's completed, what the recorded value is, and give any comments. So you can see that for all the SIFs. That is our proof test generator report. One thing I want to highlight is I did this proof test for the entire SIF. You might do it differently depending on your operational philosophy, but you can, in the project configuration, set if you want to do your proof test per SIF, per group, or per leg. And then when it comes to generating the report, you can say, I just want to list all the proof tests, or I still want them grouped per SIF. Perhaps you want all sensors proof test together, and then all final element proof test together. That's up to you, and we have the flexibility here to allow you to do that. So that in a nutshell is how I would do proof test planning with exSILentia. If I go back to my slides, if you have any other questions, we do have support.exida.com for any of your questions. If you're interested in exSILentia, you can sign up for a free trial on exSILentia.com. And you can follow exida on all the social media sites. As you can see, we're on all of them. And you can follow us for upcoming conferences to get a live demo, or just to say hi to us. But if you have any questions specifically for me, please feel free to use my email address, my phone number. I'm happy to help. In addition, we have training courses. This is just a snippet of our North America list. So you can see here we have FSE 100 courses coming up in October. We have an automotive course 211 coming up in Detroit in November, and FSE 212, which is an introduction to functional safety for software developers, as it relates to IEC 61508, and that's in Sellersville in November. This is, again, just a small snippet of our training offerings, so please go to exida.com/training, take a look at our full list. But also keep in mind we have online training courses, and these are self-paced training courses. They're at exida.com/training/online. And we have a few offerings here. You can take your time, 60 days, and go through the training course on your own time. You can always email us and ask us questions as you're doing so. But if you can't make it on site or to an open enrollment course, this is a really good solution. So we have FSE 100, we have that FSE 111, functional safety as it relates to IEC 61508. We do have a few exSILentia courses, so SIL verification and layer of protection analysis with exSILentia. We have an alarm course, and coming soon is our cybersecurity course, IEC 62443, cybersecurity software development. So these are available at any time for you to do a self-paced course. And if you have any questions about that, let us know. And that's about it for today. I'm going to send out the slides as well as a recording of the webinar. And again, any questions or answers that come down the line. Otherwise, thank you so much for attending. If you have any ideas for future webinars, let us know. We want these to be useful for you. And we would love to hear your suggestions. Otherwise, thank you.